everyone, today we're going to be teaching you a big calculus topic called mixed integrals with u substitution. In this video we're going to break down 4 different strategies you can use when tackling this topic. Thank you so much and hope you learned something today.
So before we start off with actually taking the integral, we're going to start with when to use u sub. So basically the first time that you would probably use u sub is when the integral has a function and its derivative is inside the integral. So basically you would substitute this function g of x for u, and you would take the derivative of u, which would be du, and that would make this the leftovers, which would make it easier to take the antiderivative. And the second time you would use it is when you have a integral and f of x is a weird function that you can't take the antiderivative of. So substituting u would make it easier to take the antiderivative. Okay, so we're going to start off with an indefinite integral, which is an integral without any bounds. So before you start anything, it's important to know what you're going to substitute for u. And it's kind of a trial and error situation, but an important question to ask yourself is what is du in terms of dx, and what is going to make this easier to simplify. So since this is a little bit of an easier integral, you're going to make u equal x squared plus 9. And then next you're going to take the derivative of that. So du dx equals 2x. And then it's important to move dx over here because you're trying to make it like the leftovers, du equal the leftovers, which makes it easier to take the antiderivative. So you would do du equals 2x dx. But since inside this function is only an x and not a 2x, you're able to take out the constant and put it outside the integral. So you would do 1/2 du equals x dx. So then you would rewrite it substituting u in for everything. So you would do sine u, and since right here we see that this is the leftovers, you're going to do 1/2, since you can pull it outside since it's a constant, du. And now this makes it a lot easier to take the antiderivative. So the antiderivative of sine of u is going to be it's negative cosine of u, but don't forget the 1/2 out there because it's a constant, so you still have to plug it back in. But it's important that you don't forget that you have to still plug what u equals back inside of here. So you're going to do, the final answer is going to be 1/2, negative 1/2, sorry, cosine of x squared plus 9. But it's very important, since this is an indefinite integral, that you don't forget the plus c, because since there aren't any bounds, you don't know what a constant could be, since it gets removed when you take the derivative. And that's how you do this.
So now we're going to move on to the topic of definite integrals for u substitution, and in this case the equation is going to be et over 1 plus 2et dt, where the bounds would be from 0 to L and 4. So first of all, we have to find out what u is, and in this case u would have to be 1 plus 2et. This is actually very simple to find the u, even though we have e of t, which is not very familiar concept to us, because the derivative of 1 is 0, and you just find out that 2et, the derivative of that is just 2et. So after we find u, we find the derivative of d of u, which makes it du equals 2et dt. And therefore, since we have to make it equal to the et here, we do 1/2 du equals et dt. However, there's one more step that we have to consider before moving on to the next part, indefinite integrals for u substitution. In this case, we have to plug in the bounds 0 and ln 4 into u. Why? Because these bounds are for t rather than for u. Since we are plugging back to u, we have to find the bounds for u. So when we plug it in, we have u equals 1 plus 2e to the 0, and u equals 1 plus 2e to the ln 4. Now u for u 0, the bound 0, would have to be 1 plus 2, because e to the 0 is 1, and 1 times 2 is 2, so which would make u equal 3. In this case, u equals 1 plus 2e to the ln 4 would have to be u equals 1 plus 2 times 8. Should be u equals 17. Now we have the bounds for the new integral as well as the derivative of the u. And so we plug it back in, we have 3 to 17 for half of 1 over u dt. So we plug this back into here, and this, as we see, is e dt. We plug half du into there. And the bounds, as we found, are 3 and 17, and eventually we just take out the half as we got before here. So moving on, all we do is find the integral of this, which becomes half of finding the integral of u to the negative 1 is very simple, as it is ln u. And 3 to 17, multiply this by half. So eventually we just get ln of 17 minus ln of 3 over 2. And from here, you have to use a calculator to find out what ln of 17 and ln of 3 is, and that's the furthest you could get without using a calculator. Thank you.
Hi everyone, so the next topic we're going to cover in this video is how to approach integrals that look like this. So at first glance, this looks like a very complicated integral, and there obviously is not a way to use u substitution with this particular problem. So we're going to be talking about how we can simplify seemingly complex integrals and make them actually really easy to solve. So today what we're working with is the indefinite integral of 3x to the 4th minus e to the x over 2. And the first step to solving this equation is remembering a basic fraction rule. So 3x to the 4th minus e to the x over 2, as we know, can actually also be written as 3 halves x to the 4th minus 1 half e to the x. This is a really basic part of just breaking down fractions, recognizing that you can break up the numerator when the denominator is the same. So this is the equation that we're going to be working with, because when you just have a basic subtraction problem, it's a lot easier to find the antiderivative of that. So now that we've simplified this equation to get 3 halves x to the 4th minus 1 half e to the x, all we have left to do is a simple antiderivative problem. So since we have x to the 4th over here in this equation, we know that our variable here is going to be x to the 5th with a constant of 3 over 10. And then we can move on to the second half of this equation, which is 1 half e to the x. And we know that that is just going to be 1 half e to the x, which is the same thing because the derivative of e to the x is e to the x. So now we've simplified our equation to have this. This is the antiderivative of our original problem, which was 3x to the 4th minus e to the x over 2. And we have at this, and as always, when we are working with indefinite integrals, we have to remember to add c. Thank you so much.
Hi guys, I'll be teaching you trig identities with integrals. So there's three. There's inverse sine, inverse secant, and then inverse tan. So there's actually tricks to memorize these because there's no easy way out. You need to memorize these three trig identities. So for sine, this s right here can help you remember that there's a square root and a subtraction right here. For secant, it's almost the same, however, you need to remember an absolute value, and this s can remind you that there's a square root right here. You need to flip these two, and there's a subtraction. So you need to flip these compared to this one. And for the tangent, this t right here can represent this plus sign right here. So these are the three tricks that can help you remember these trig identities. And now, on to an example of a problem. So now I'll give you an example of what a trig identity function looks like. So with this indefinite integral, you can see that 1 plus x squared is what tan is. Tan, the inverse of tan is this. And so you just need to recognize that this is one of these equations, but there's a 2 in here, which means that the constant will be right here for the antiderivative. So for this one, the antiderivative would equal 2 inverse tan, and then since this is an indefinite integral, it's plus c. So that's the answer.
Thank you for watching our video. Good luck in CALC AB.